What we're going to talk about is rapid earth fault current limiters. So just a bit of background on it. Black Saturday bushfires in February 2009 in Melbourne. So there was a massive bushfires, which probably most people know about. Lots of hot days above 43 degrees, peaking at 45. There was 400 individual fires, 358 firefighters deployed. But worst case was there's 3,500 structures destroyed and nearly 12,000 head of stock lost. This is probably topical at the moment when you see the bushfires we're having in New South Wales and up in Queensland. So from that, Victoria developed a Bushfire Royal Commission, and they did a review on a lot of the instigation or the starting of the fires. So arson with some of the fires were deliberately lit. A man allegedly using power tools in a caused sparks to cause it. And then one of the things that started the rapid earth fault current limiter investigation off was an incorrectly swirl line was ripped down at Kilmore East substation. So it fell down and created sparks and initiated the fire. So the electrical cause of the fire, wind speeds reaching their peak, incorrectly rigged swirl lines ripped down at Kilmore East, sparked a bushfire that would become the deadliest and most intense firestorm ever experienced in Australia's history post 1788. I'm not sure if that's the case anymore with the current ones happening around Queensland, New South Wales. It was estimated that the energy released in the storm in the Kings Lake Maryville area, that's just north of Melbourne, was equivalent to around 1,500 Hiroshima-sized atomic bombs. So a huge amount of energy released in those fires. So from the Royal Commission, they ended up with some recommendations. The accepted recommendations require the implementation of a range of initiatives over a 10-year period to reduce the bushfire ignition risk by 2/3. That's a pretty substantial requirement to actually get bushfires down due to the network or the distribution networks. The outworking of these recommendations through the Victorian Bushfire Society created a task force, and that ended up in the installation requirement of 22 rapid earth fault limiters in substations by December 2022. As far as I'm aware, the first one's going to go in June next year, and I've been doing some investigation work around the compliance of the load side of the implementation of the rapid earth fault current limiters. So the new standards are specified for line works within the defined areas. So they're picking on certain areas within the Victoria network which actually caused the faults or where these ones occurred, in the hope that they can actually reduce the risks around these areas. So they ended up developing a standard with specifications for the rapid earth fault current limiters. So it must reduce the voltage in a faulted conductor in relation to the station earth when measured at the corresponding substation for high impedance faults down to 250 volts within 2 seconds. So their standard system is just a TNS system with no fault limitation. So now they're aiming to get that voltage down to 250 volts. Next one was the reduced voltage on the fault conductor in relation to the station earth. So we measured to the corresponding substation for low impedance, which is 1900 volts in 85 milliseconds, 750 volts in 500 milliseconds, and 250 volts in 2 seconds. So now they've gone from a high impedance system to a low impedance system, so where the currents are on the low impedance are a lot higher. And during the diagnostic tests, fault limit, they found that the fault current needed to be limited to around 0.5 of an amp or less. And one of the key issues is the thermal energy, which actually creates the spark and the fire, limited to 0.1 of an amp per second squared. So that's the current distribution in the ground on the faults. Just a bit of background. So rapid earth fault current limiter is a device which reduces the risk of fires by power lines installed in stone substations between the transformer and neutral connection, rapidly limiting the earth that is released to a certain type of power lines known as earth faults. The RAF ESL device trialled on the 22 kV network, and they're looking at other voltage in the future, but probably that's probably 5 to 10 years away while they sort out the 22 kV stuff they're actually working on now. Some of the technology is a ground fault neutralizer, arc suppression coils, the solid state current limiters, and there's obviously other combinations around as well. So we'll go through the technology of these things as well now. So this one's a arc suppression coil or a ground fault neutralizer. So what it is, it's an inductor hooked into the neutral connection, and then it's got a specific controller to control it. So back in the original days, they were called Peterson cells. These ones had, the modern ones now, the Peterson cell was a fixed inductance which tried to match the line capacitance. These ones now are dynamic, so they can actually change the inductance as the system network changes. Right, so the key things about an arc suppression coil or ground fault neutralizer. So arc suppression coil is an inductor that connects to neutral ground, and the ground fault neutralizer is just a proprietary design based on additional technology included in it. The inductance is tuned between near resonance at the 50 Hertz with the total network capacitance. In this state, the connection between the neutral and the earth has a very high impedance. So earth fault currents are used with less than 10 amps. So their aim is to get it less than 10 amps, much the same as what we do with our IT earth systems. So on this system, they ended up with a 500 milliamp inductor and a capacitor, or variable capacitor, to tune the network. And the tested networks at the settings around 10 amps, the parallel capacitor provided about 70 amps of capacitive current. So this is where we're talking about the capacitance between the line, which can be up to 200 kilometres long, and the ground, which where the current flows through capacitance. So the ground fault neutralizer, this is just a three-phase diagram of it. So you can see, where is the pointer? So you can see up in the top there, you've got the 3 monitoring CTs. The red is your residual current compensation. So in the green there, you've got the capacitive currents that would flow, and the residual current compensation is done by the unit, by the ground fault neutralizer to align the network capacitance so you get a zero current flowing via the capacitance in the network. So second type is the solid state fault current limiter. It's basically a high voltage switch inserted in the line from the ground to neutral. So it's a group of IGBTs, which like this one here is the one we looked at was a 6 insulated IGBT control switches with an RC network, provided over voltage protection via oxide resistors. The system could be set to a neutral to exceed the threshold. The solid state operates in microseconds, so we'll have a look at that in a minute as far as the speed of the operation. And the current transformer provides an analog feedback back into the network, so which then operates into your tripping circuits or your circuit breakers. So up on the diagram, again, it's the NER, the NER has been replaced with a series of IGBTs with a controller, and then you got your capacitive network around that and your over voltage protection. So it basically looks like hooking in a inverter controller in for your neutral connection. So this is just a diagram for your standard TNS system, which is the MEN, which are used in distribution networks. So follow the red arrow. The current flows through the capacitance. On this one here, when a ground fault occurs, the cable falls to the ground, creates the current path back through. So that's basically what happened at Kilmore, but on a different line, where the cable fell to the ground, initiated a spark, and then caused the fires. Everybody should be familiar with this one with IT earthing. So again, even with 10 amps limited, or up to 10 amps, the system still has enough energy in the I squared A per second to create the spark and the fault to create the fire. So this is just a diagram. So this one shows now the capacitance through the ground. The residual current compensation on the previous diagram cancels out any ground fault currents associated with that. And then the ground fault neutraliser. So the ground fault neutraliser, then you can see there's no spark there because the inductance has matched the capacitance and the fault currents to actually cancel the fault. So this is the sample test they did at Kilmore substation in Victoria. So on the diagram you can see we're operating here. We're at 12 kV. One of the lines, the red line, goes down, hits earth, and the corresponding phase to earth voltage then rises on the other lines up to 22 kV roughly, which is the standard typical thing you would see in a IT earthing system where you've got a phase to ground earth fault. The insulation levels have to be increased. And then once the fault gets cleared, then the system turns back to normal. One of the key things here is that the time that they're using in here is going to be an extended time where we're used to clearing under a fault fairly quickly. The distribution authority can have up to like 30 seconds clearance time to actually allow their network to detect, do a directional test on the faults and then locate that fault and clear the fault rather than tripping the substation. So this is just a diagram of what they're planning to do. So standard operation, the blue phase goes to earth, the red phase voltage to earth goes high, and then it comes back to normal operation. But the key one here is this time here, 20 to 30 seconds for it to clear. So it's going to be holding that voltage for a longer period of time. So for the analysis they use for the typical wire down to ground, so they use the 3 metre contact period, or contact length. So when the power line falls down to the ground, they've estimated that the standard first touch is around 3 metres, and that gives you a current density of about 0.15 amps per metre. So what they did, they took that and then converted that into, which is 0.45 for the 3 metres. So they took a higher value of 0.5 amps for the worst case wire down fault. And that's what they need to achieve to prevent grass fires. A standard grass fire can take many seconds to clear, or sorry, to ignite. So if you look at the top picture, that's a picture of a ground where it's gone to ground, it's hit and the ground with the aerial line, and it sat there for a period. It's ignited it scorched the grass around it, but it actually caused a fire. So the next thing is the video. It actually shows you a test where the power line drops to the ground, and you can look at and see what the sparks occurring with that. So you can see from the ground fault neutraliser the sparks that occurred, the amount of damage to the grass or the scorching of the grass was next to nothing, because the ground fault neutraliser or the RFCL system actually stopped the current flow. So they come up with the performance standard for a low impedance fault, 85 milliseconds. The fault must be limited to less than 1900 volts, 500 milliseconds to get down to 750, and then 2 seconds for the 250. Just the definition of the low impedance fault there is 400 ohms for a 22 kV network. So this is results of some of the tests they did. So what they were trying to do there is verify that the times actually got down far enough and then cleared the voltage. So you can see in the graph there's the voltage there, right? So even though they're about, that's what they measured at the fault, but their timing is down below the 500 milliseconds for all those tests for the arc suppression coil and the ground fault neutraliser. So when we compare that to the voltages associated with touch voltages for 3007, right? On the graph, the blue line is what the RFCL will clear to, and the red line is what AS3000. So basically the RFCL won't give us any touch potential benefits, so our systems will still need to comply. High impedance fault. So the RFCL must detect the fault within 1.5 seconds. Within 2 seconds, it must be down to 250 volts. During the tests, to confirm the fault is sustained, not to identify which power line. So they did the test, they come up with less fault current than less than 0.5 of an amp, and the I squared T, which is the energy that's caused the ignition, must be less than 0.1 of an amp squared per second. So you can see here on this is a graph of the ignition. So on the graph, there's your I squared A, and then for the 0.5, we have to operate or clear within 400 milliseconds. So their system is proposing to shut down the power within 400 milliseconds of a ground fault being occurring. So when they did their tests, right, they set the detection time at 0.5, and then the clearance times they got were around about 0.2 to 0.3 300 milliseconds. So that's super quick, even for our standards, what we use on mine sites. So with the 15 k ohm, this is where they set like a medium level ground impedance. The time to detect was down at 0.33 on one test and 0.17. And then the solid state RFCL, it cleared in less than 5 milliseconds. So their protection now on this line, if they, depending on which way they go, whether they go with the ground fault, it's going to be clear somewhere less than 5 milliseconds for a solid state, or they're going to be down at 0.33 seconds for a ground fault neutralizer. So this is just a diagram of the solid state one, where the fault's out in the field, comes to the ground fault, returns back to the earth, and then the IGBT system shuts down and blocks any current flow. So they got limited to 800 milliamps in less than 5 milliseconds. So they're talking about very quick times now for clearance of faults and limited ignition. So this is out of AS60479. This is your body impedance curve. So you can see that for a ground fault neutralizer on high impedance, it's not going to offer a lot of protection for people, but the solid state one, it doesn't even appear on the graph because it's that fast. So this graph again is back to the ignition energy. So when we compare our stated currents for 500 milliamps, 500 milliseconds from 2081, right? We're here in that orange curve, and the blue curve is below that. So their protection is probably going to operate a lot quicker than what we can detect. So any fault in our system, we probably won't detect, and will be blocked by their system. So this is just like a typical mining diagram. So you got your 22 kV coming in. I'm assuming in this substation we're just switching through a circuit breaker, and then we're feeding it out to a machine. So on the machine we have a fault. We've got our earth leakage protection stuff set in here. It's not going to work. We just took the upstream protection from the ground fault neutralizer or even a solid state one won't let our system clear. It'll block the current. You won't detect the ground fault, and you probably won't even know it's happened. So one of the jobs I've been working on, we've been looking at the assets. So when they actually implement this stuff, we've been looking at the installation as far as compliance to now having the phase to earth fault at a higher level. So this particular installation was a Schneider RM6 unit, so it had sufficient clear voltage rating on their VTs so that they were okay. Sorry, that was the CTs. The VTs are fine as well. They've got 24 kV. And additionally, you need to look at your surge arresters. So basically the outcome of the investigations we worked on the RM6 units, it was actually compliant and Schneider actually issued a certificate for it to say that it was all good. One of the main issues they come up with was the cable selection, so under 1429. So the cables are obviously rated for 12/22 and then 1933. So some manufacturers will give you a certificate to say that if you can operate those 12/22 cables on a network, which has a ground fault limiter in it, and as long as you clear within time, that'll be fine. But the clearance times typically are around less than 10 seconds, so you don't get any cable damage. This system that they're putting in now is going to have clearance times of up to 30 seconds. And then they've also mentioned in trials that when they're doing their testing, they're going to be up for 10 minutes. So the standard cabling, even if it would work for us or anybody, in less than 10 seconds is okay, but not in these installations anymore. So I guess what does that mean for us? REFCL has rapid clearance times. The bigger driver of all this is going to be the ignition energy. So you can look at the curves, look at the clearance times. Potentially we can't respond on the downstream side to any of the faults. I've actually spoken to one of their experts in Melbourne for the REFCL and asked him about how we're going to coordinate protection from upstream to downstream. His answer was, we don't know. We haven't installed one yet. We'll work it out when we get there. So it doesn't sort of provide a lot of guidance on that point at the moment. So your standard ground fault, whether you're using a summation in a circuit breaker or earth leakage, RCT, CT on MEN link, they're not going to work. Sorry. Transfer voltage will still need to be controlled under your current protection schemes because based on the type of system that goes in, it may reduce it, but it's unlikely. Equipment selections will still be based on IT systems. Isolation transformers, we looked at them as far as isolating their network from ours, so put an isolation transformer in. But the problem with that is you can't get far enough away from their system to get a remote earth to get the earth transfers because in this case this is a residential area. Basically on mine sites you may be able to do something. And then I guess with the legislation going forward in Victoria, it's going to move into New South Wales at some point, and then they'll be looking at what they do. So any supplies coming into the sites at the 22 kV and potentially in the future at the 66, they may be looking at doing something, as well as potentially changing the legislation so that the on-site stuff also has to comply with this legislation. So any of your internal distribution networks have to comply so they don't cause any fires and stuff as well. And that's me.